my people. It's probably going to be the last one on volumes of solids of known cross-section. Let's go ahead and jump right into the next problem. We have y is equal to x, y is equal to 2 minus x, and x is equal to 3. Okay. Let's go ahead and, again, let's go ahead and scale it -5 to 5, -5 to 5. Each unit is 2 boxes. Let's go ahead and graph our identity function. Our y is equal to x. Okay. And then we also have 2 minus x, which is, let's go ahead and color this one before we forget. Okay. Let's go ahead, 2 minus x, that's negative x plus 2. So it's going to come through here, and here, 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 and here. And so it's going to look something like this. Okay. And we're going to make it green. Now, we also have x is equal to 3, and that is this vertical line. Okay. Now, that means that our region that is going to be the base for this solid is going to be that triangle created by those 3 graphs. I also know that my cross sections are going to be perpendicular to the x-axis, because they all are on this worksheet that I'm working off of. And I want my cross sections to be rectangles. And this one, the height is twice the width. Okay? And every time you have rectangular cross sections, you'll be given some type of information like this. Okay? And so if the height is twice the width, I know that height is 2 times the width. Okay? And if the area of a rectangle is width times height, and I know that my width is going to be my s of x, right? It's basically I need it in terms of width, not in terms of how far it comes off the page. So it's going to be 2w squared. So for this particular one, we're going to have a coefficient of 2 sitting out in front, or a constant of 2 sitting out in front of the integral. Okay. Now, my limits of integration are from this point of intersection to this artificial ending of the region here at x is equal to 3. So 1 to 3 are my limits of integration. Now I simply need to find my s of x. My s of x, basically this distance right here in terms of an analytic expression in terms of x, is going to be pink minus green, right? So it's going to be x minus 2 minus x, or x minus 2 plus x, or 2x minus 2. Now, that means that my s of x squared is going to be 2x minus 2 squared, or, you know, if you want, 4x minus 1 squared. Because if you pull the 2 out, the 2 as being squared is 4, right? Alrighty, let's go ahead, and if this right here is my s of x squared, I can go ahead and set up my integral. I'm going to go from 1 to 3. I know that my constant is 2. I know that I have 2x minus 2 squared dx. Now, I know that when I simplify, I'm going to have that 4 right there. I can pull it out in front and combine it with the 2 and make 8. And then I'm going to have x minus 1 squared, which is x squared minus 2x plus 1 dx. When I integrate, it should be relatively straightforward. I have 1/3 x cubed minus x squared plus x, and I'm going to evaluate it from 1 to 3. Now, my limits of integration do not include 0, so I'm actually, in terms of this one, going to have to plug in both numbers, right? Now, when I plug in 3 cubed is 27, but 1/3 of that is 9. 3 squared is 9 plus 3. And then, almost forgot to put the 8 out in front. Very, very important. 1/3 minus 1 plus 1. Okay. Now, this 9 and negative 9 cancel. This negative 1 and this positive 1 cancel. And so what I have is 3 minus 1/3. That is 9/3 minus 1/3, which winds up being 8/3. 8/3 times 8 is 64/3. And that's kind of interesting. That was actually the answer to one of our previous questions, right? Let's go ahead and move on to the next one. We're going to go a little bit quicker in this video because, I think we can. We've actually had a couple problems worth of practice. Now this one is going to be dealing with quadratics, okay? And so my first one is y is equal to x squared minus 2. That should be relatively simple. That's the parent function, just move down 2 units. Now the next one is unfortunately 3 transformations, but they aren't all that difficult. I want my cross sections to be equilateral triangles, and I want it to be perpendicular to the x-axis. Equilateral triangles, remember, has a constant of √3 over 4. Now, let's go ahead and do our scale as we normally do, -5 to 5, -5 to 5. And so, okay. X squared minus 2. Now this first one should be relatively simple. It's going to start right here. It's going to go over 1, up 1, over 2, up 4, right? Over 1, up 1, over 2, up 4. You can use the symmetry to help you. And then, of course, over 3, up 9. Well, that's actually going to be 2 units past the edge of our Cartesian plane, but we know that basically it leaves the Cartesian plane before getting to 3, which is a useful piece of information. And so we will sketch that roughly. Okay. Now the next one, I'm going to take, remember, I have 2, 2. This is my vertex, right? Because vertex form. And it hasn't really changed shape except for the reflection, right? And so it still should move out and away from the vertex in the same ratios as the parent function and as the one right here. So over 1, down 1, over 1, down 1, over 2, down 4, over 2, down 4. Now, for our purposes, that's really what we were looking for. We were looking for that region right there, the overlap of those 2 graphs, okay? And so we have this graph coming in like this. We have this one up through, and we have that little sliver right there as our region that forms the base of our solid. I know that my cross sections are going to run perpendicular, okay, to the x-axis. And I know that I have equilateral triangles. The only thing left for me to discern is the limits of integration, which of course come from the points of intersection. I can read it off the graph. I know that they both go through 0, -2, and 2, 2. I could, if I was just, nervous or whatever, I could basically do it analytically, right? And you get, x squared minus 2 is equal to negative, x squared minus 4x plus 4 plus 2. So that's x squared minus 2 is equal to negative x squared plus 4 minus 4 plus 2, so minus 2. The minus 2's go bye-bye. and I'm going to get 2x squared minus 4x is equal to 0, or x squared minus 2x is equal to 0. That factors x minus 2, blah, 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 and x is equal to 0, and x is equal to 2. Those are my points of intersection. Or, like I said, you can just read it off the graph. That means that my limits of integration are going to be 0 to 2. They're equilateral triangle cross sections, so I need to remember my root 3 over 4 out in front. Okay? And now I need my s of x. Well, my s of x is going to be the green minus the pink. Okay? Now the green minus the pink is green, pink, right? Now, when I shoved everything over to the left-hand side, I got pink minus green. All I would really need to do is basically flip that difference in order to make it the other way. Now, if you actually, if you don't trust yourself and you actually want to do the analytic work, we can go ahead and do it over again. That's fine. Now, our green, we know that our s of x is going to be green, negative x minus 2 squared plus 2, right? Minus my pink, x squared minus 2. Well, this one winds up being negative x squared plus 4x minus 4 plus 2 minus x squared plus 2. Again, I see that negative 4 and positive 4 cancel out, and I'm left with 4x minus 2x squared. That means that my s of x squared is going to be 4x minus 2x squared squared. Or, again, if you want 2x minus x squared, quantity squared, that can become 4. Or you can even pull out an x, right? A 2x, so 4x squared, and then x minus 2 squared is, x squared minus 4x plus 4. And that winds up being, you can pull the 4 out in front and just leave this right here, right, as your s of x squared. Okay, let's take that back to our original. That means that we have 4 times x to the 4th minus 4x cubed plus 4x squared dx. That means that when I pull that 4 out, it's going to cancel with the 4 in the denominator right there. I go 2 to 0, and I have the x to the 4th minus 4x cubed plus 4x squared dx. And when I integrate, I'm going to get 1/5 x to the 5th, x to the 4th, plus 4/3 x cubed from 0 to 2. And when I plug in 2, I'm going to get 32/5 minus 16. And then 2 goes in here, makes an 8. 8 times 4, of course, is 32/3. And then when I plug in the zeros, I'm just going to get 0. And so basically what I need is I need a decimal approximation of that. I could probably work it out by hand, give me a denominator of 15 and a radical in the numerator, but let's go ahead and not do that, okay? Let's go ahead and just, actually, remember, we need to go ahead and do the constant out in front. So root 3 over 4 times the integral from 0 to 2. And this one will simply be, we'll call it 4 times x to the 4th minus 4x cubed plus 4x squared. I need to go ahead and put in another parentheses and then times dx. Okay. Now, remember that you can go over here and do it this way instead. Now, I know that the green one is going to be on top, so I want that to be my y1. Okay, so negative x minus 2 squared plus 2, right? And then x squared minus 2 is going to be my pink, going to be my y2 because it's the one I'm going to be subtracting. Let's go back to here. Let's go ahead and do the root 3 over 4 times, and of course this is just checking our answer, making sure that we didn't make any mistakes when we were sort of doing our analytic work. Squared dx, and boom. Okay, identical answers showing that we didn't make any mistakes when we did our analytic work, and our answer, our volume, is going to be 1.848, okay, approximately, units cubed. Okay, now, last one, let's do one more, okay, and this will be a cubic and a linear. Let's see, y is equal to x cubed minus 4x. Y is equal to x, and we have another stipulation that x is greater than 0. So we're looking for a region between those curves that is, over here on the right-hand side. My cross sections for this particular one says it's going to be squares, so we only have to basically plop a 1 out in front, or just, of course, leave it alone. X-axis. Now, y is equal to x cubed minus 4x. Has 3 solutions. It is an odd function. It has symmetry. Okay, it has y-axis symmetry. I mean origin symmetry. And its zeros are at -2, 2, and 0, the origin. Now the reason that I know that is it's pretty easy to factor, right? X cubed minus 4x is the same as x squared minus 4, and y is equal to x plus 2, x minus 2 shows us that those are the zeros, right? That's just the function in factored form. Let's go ahead and do that. Now, if you wanted to actually, find and accurately plot the maximums, because it's going to be cubic, it's going to come up and then go like that, right? Because it's cubic and it has a positive leading coefficient. If you wanted to accurately find, those maximums, and the maximum and the minimum, of course, it'd just be y prime is equal to 3x squared minus 4, and you set that equal to 0, and you get x squared is equal to 4/3, or x is equal to plus or minus 2 over root 3. And of course, 2 over root 3 is 2 over 1.732, so it's just a little beyond 1, okay? Let's go ahead and plot put both of those into our calculator, okay? I know that it's going to be x to the, actually, let's go ahead and put that into y1, x to the 3rd minus 4x, and then x, okay? Let's go ahead and graph it on this the same window a window basically the same as the way we've scaled our graph, and we see there we go. Okay, and notice that the max and the min are just a little outside of 1 and -1. Okay. So let's go ahead and graph that. Now, if we wanted to, instead of doing the work, let's go ahead and find that minimum value. Okay, minimum. Okay, and you have 1.155 and 3.079. Negative 3.079. Okay, so basically, the minimum is right about here, okay? And here's the 0, and that makes it kind of nice. So that means because of the symmetry, you have a maximum over here, mirrored kind of over there. And your graph looks something like that, okay? Now, we also know that we're dealing with the identity function here. Hurrah, hurrah. And so it has 2 points of intersection that give us this region where x is positive. Okay. And okay. So we recognize the fact that the identity function is going to be the more positive one for our purposes here. We also know that our cross sections are going to be perpendicular here. Now, what we need to do is we need to find those points of intersection. Well, here's the thing. If I'm looking for points of intersection, I simply have to set them equal to each other, right? So that's x cubed minus 4x is equal to x. Well, that means that it's x cubed minus 5x is equal to 0. Well, notice that this point of intersection is just a little outside of 2 because the points of intersection are 0 and plus or minus root 5. Okay? When I factor this, and it's going to be x squared minus 5 is equal to 0. Okay? Now, that doesn't make me very happy because I don't like irrational numbers as limits of integration, but is it doable? Absolutely. Okay? And I know that I'm going to go from 0 to root 5, and of course they're squares, so I need to have a 1 out in front. The next thing that needs to happen is I need to find my s of x. Well, it's going to be x minus this, okay? And so what happens is you're going to have x minus x cubed minus 4x, the whole quantity squared dx. And it's going to look relatively familiar because it's just going to be the negative of that right there, okay? Remember to distribute the negative to both terms, and you're going to have 5x minus x cubed squared dx. Now, I could go ahead and do that by hand. The idea of foiling that is not really that big of a deal, but the prospect of plugging root 5 into several of those does not make me exceedingly happy. So what we're going to do is we're going to go ahead and do it by means of our calculator, okay? And so we're going to get our integral. Now we don't have to put the c value out in front because remember it's a square, the c value is 1. And I have 0 to root 5. Now I did plug the cubic into y1 and the linear, the identity function, into y2. So I need to remember that. Not that it really matters because you're squaring it, but, you know, just for the sake of due diligence and all that sort of fun stuff. Because, you know, not every integration problem, you are squaring it, so sometimes the order does matter. And what we're going to find here is, voila. Okay, voila. It is 21.296 units cubed. Okay. Guys, I went through all of the formulas for those constants that set out in front. We've discussed how to find our s of x, which is basically our expression in terms of x of how we measure the length or the length of the cross section as it goes through the region. And we've worked about 6 examples here, and we worked a couple more examples in the lecture. And of course, there's those other videos that are in the playlist as well. I think that's sufficient for now. Like I said before, if you want more, please ask. But I don't want to make unnecessary work for myself, and I also don't want to drown you with resources, because sometimes if you have too much, you can not know exactly where to start. So If you have any questions, please do shoot me a message or shoot me an email. I've actually been bad about checking my email because everybody's been communicating with me on Teams. That's probably the best way to contact me. Yeah, I'll look forward to hearing from you guys, and I'll look forward to chatting with you on Friday. Take care.